when we define my dot product, I will just model this from the way we introduce the dot product in 3 dimensions. And in terms of coordinates, the actual formula for finding the dot product is so simple, you can't make any mistakes with that. Normally you do like this, but I will give it to you, I will present the formula now in the general scope of n-dimensional space. Remember, in the general scope of n-dimensional space, we operate with n tuples, or with column of numbers. So if I have 2 vectors, which basically is synonym for the column of numbers these days when I say vectors. So here's my column of numbers, A1, A2, dots hiding the most of the terms, and it is conventional to write the last one to indicate how many of them we're looking at. So if I have vector A like this, if I have a vector B like this, again with the components, B1, B2, Bn, again from Rn, dot product, we normally write something like this, just 2 vectors and a dot in between, and I will, in order to finish this formula, I will open some extra expression which is also used for the dot product, but for now I just ask you to disregard that. It's just irrelevant for now, the way it is written like this. It's just the way we write the dot product. This one is the one you're going to use in the tutorials. This one will gain some sense in 3 to 5 weeks' time. So for now, you can copy that if you want. You can just leave it because this will be uploaded on the website anyway. But that's the primary way we normally write dot products. But computationally, this is as simple as this. We just multiply my vectors in a per component way. We multiply the first component here with the first component here, second with second, last with last. We add everything up. The expression we come up with, that's the number which stands for the dot product. If you have any doubts what is it sitting in front of you on the screen, here's the simple example. If I have a vector A with 4 components like this, 1, -1, 2, and 3, and if I have the vector B with components like 2, 1, 1, and -1, dot product for these 2 vectors, this is the simple task even a monkey can do. You just have to sub in the numbers. yes. There's no any thinking involved in this, in the computing the dot product. You just sub in the numbers and use your calculator, either the electronic calculator or this calculator, whichever you prefer. Here's my substitution, 1 times 2, -1 times 1, 2 times 1, and the last one. We're looking at the 4-dimensional vectors, so we need the 4 terms here, and it happens to be 0. I didn't do this arithmetic, but I did it before. I think it is 0, in fact. So let's just see 2, take 1, it's 1, plus 2, it's 3, take 3, it's 0. That's truly 0. Normally, when you look at the dot product, you expect some properties from it. And the properties you expect, they are expectable. Forgive me this tautology. They are quite expectable. The properties which you expect from any other product, like a numerical product. You can expand the brackets, you can flip the factors around, you can multiply the scalars across these factors. These are the properties which can be formally proved. And I think lecture notes have this proof. I'm not going to put this proof right now. I don't think it's really that much of importance. But I need to list the properties anyway because I'm going to use them on the next slide. So I will list them. If you're wondering about the way why this is so, I don't think you will. I mean, as soon as you use the definition, it will be more or less straightforward why this is so. But if you have any difficulties establishing that, lecture notes have the detailed account of this argument. But normally we expect this sort of properties from the dot product. We expect that we can flip the terms around. A times B is the same as B times A. In a high mathematical language, this is sometimes called the commutative property of the dot product. This is the property number 1. This is the property number 2. The property number 2 says that you can take the scalars across the dot product. This bracket, that's the number. If you multiply this number by another number, you can take this number across the factors individually, and that will not alter your dot product. I draw your attention to the fact that even though I use the dot here and I use the dot here, these two dots, they mean totally different operations. The meaning behind these dots is totally different. The dot here, it's a dot product between the vectors, whereas this dot, what is this dot? I? Which multiplication again? It's ambiguous term, scalar multiplication. Can you be more specific? I mean, I can't pick up the answer from the murmur you're giving. Anyone like who's brave enough to voice it for the whole class? What's the second dot represents? Scalar multiplication. You said when I hear the term scalar multiplication, two things come to my head. One of them is when you multiply by scalar a vector. It's one thing which we normally term scalar multiplication. The other thing which we normally call scalar multiplication is multiplication between two numbers, like a regular numerical multiplication. So which of those two you were meaning when you said scalar multiplication? First or second? Who goes for first? Who goes for second? Well, this part wins, actually. Yes, it's a regular numerical multiplication. This bracket, it's no longer a vector, it's a number. Look at this. So this dot, it's a numerical multiplication, not the scalar multiplication of a scalar and a vector. Anyway, the other property we expect from the scalar product is what is called, officially it's called the distributive law. Unofficially, this is something which lets you expand the brackets. The third property says like this: when you dot product a vector with the sum of the other two, you can do this individually and then sum up the numbers. Officially, this is called distributive law. Unofficially, like I said, it is something which enables expanding the brackets with the dot products. Again, the same question to you. This number plus here and the number plus here, the same symbol, but they symbolize totally different things. Left-hand side plus, it stands for vector addition. The right-hand side plus stands for numerical addition. You see how nice it goes? I mean, we don't have so many symbols to distinguish them every time we write. It will be quite a nuisance if we start doing that. But in our heads, we always have to keep this in mind, that the same symbol may mean different things depending on the context where you use that symbol. Anyway, that's all there is to the dot product from the definition point of view for the n-dimensional space. Of course, the dot product, the first thing which is connected with the dot product is the length, something I mentioned earlier. Dot product gives the length another angle. Well, not a big, it's not a different angle, but slightly maybe different. Length of the vector, in terms of the dot product, it can be computed like this. It's a root, square root of the vector dot product with itself. If you do the arithmetic, you will come up with the regular formula for the length when you sum up the squares of the components of the vector. It's just another link which connects these two concepts, length and dot product. Okay, the main reason actually we look into the dot product, it's the reason is this. In 3 dimensions, dot product gives you the concept of an angle. In fact, I have a slide for that, which is called the angle. And let's just look into that.